Now we will consider how we can perform different inverse operations, because this is very much essential, because after some transformation how we can bring back the object in its original shape or original positions. So this is basically the inverse operation. Now let us first understand how we can achieve that. In case of translation, we have already discussed that if initial positions of the object is at P x y, then after translation the corresponding point on the object is at P dashed, which is at x dashed y dashed, and the translation was taking place along the vector v, and we have represented this translation operation as T v. The idea is, if we operate this T v, on any object point P, then we will get the corresponding translated point, transform point P dashed, and v is specified from this as T x I cap plus T y j cap, because T x is nothing but the amount of translation along x direction, and T y is amount of translation along y directions. So the inverse translations will be such that if this inverse translation T v inverse that is operated on P dashed, then we will get back P. So this is the inverse operation. In this case, the inverse operation is nothing but the translations in opposite to V. So we can say this P dashed is nothing but T minus V operated on P. So the inverse is nothing but translating P dashed in opposite to V, that is T minus V. So we are saying that T V inverse is nothing but T minus V. So the matrix operator is very simple. V is specified as T x I plus T y j. So what is T minus V? T minus V is that matrix which is 1 0 minus T x, 0 1 minus T y, and 0 0 1. Because it is very simple that in this case what is minus V? Minus T x I minus T y j. So this is T x T y, in this case this is minus T x minus T y. So this is the inverse translation. Now what happens about inverse rotation, inverse of rotation operation? Let us consider the earlier rotation operator. This is x direction, this is y direction, and we have specified that the object point P x y is rotated through an angle theta, and the corresponding positions is at P dashed. And we have used the convention that rotation in opposite to in anti-clockwise direction is positive, and if it is in clockwise direction this is negative. So if we want to bring back the object point P dash to P, then we have to give rotations opposite to the earlier rotations. So earlier we have said that on P we have operated R rotation with respect to origin through an angle theta, and we got P dashed. So the inverse operations will be, P will be obtained from rotation with respect to origin, that operator, that is R 0 theta, its inverse of that, and that is operated on P dashed. Now how this will be obtained? So this is nothing but rotation opposite to earlier rotation. So we can say that rotation through an angle theta, its inverse, this is nothing but rotation with respect to origin through an angle minus theta. So if you rotate opposite to the earlier direction, then we will get the same effect as inverse of this rotation. So this is inverse rotation. In the same way, if we scaled a particular point on the object, suppose we are considering this object. After scaling, this point is here, say for example, this point is scaled up to these positions. So, inverse scaling is opposite to that, it is just inverse of that. So, if Sx is the scale factor, then inverse will be 1 by Sx, because scale up is multiplying the object point by some constant factor, by some constant, and inverse operations will be just dividing that the object point by some constant. So, if Sx is the scale factor along x direction, its inverse will be 1 by Sx. If Sy is the scale factor along y direction, its inverse will be 1 by Sy. So, in this way we can obtain the inverse operations, and these inverse operations are very much essential in case of composite or complex transformations. For example, we want to give a series of operations, like suppose we want to represent the rotation with respect to some arbitrary pivot point, say hk, say let it, this is a hk. Suppose instead of describing rotations with respect to origin, we want to describe rotation with respect to some arbitrary pivot point A, whose coordinate is hk. So, in this case, initial positions of the point P is xy, and after rotation with respect to this pivot point through an angle theta, the positions of the point P dash is x dash y dash. Now, how we can represent x dash y dash in terms of the known quantity? In this case, the known quantities are x y, definitely the object point, and the arbitrary pivot point hk, and the angle of rotations theta. So, in this case we need composite transformations. How? We know so far the rotation with respect to origin, we do not know the rotations with respect to any arbitrary point. So, what we have to do, we can achieve this with the help of either translating the coordinate to this point and we can describe the rotations, or we can translate A to origin. So, after translation A is now becomes the coincident with the origin, and accordingly that translations will be applicable to every object point. Now, after that we will perform the rotations with respect to the origin. So, the steps in this case are as follows. Step 1, translate A hk, which is the arbitrary pivot point, to origin 0 0, and this translation is applicable to every point. Step 2, then perform rotation with respect to origin through an angle theta, which we require to find out. So, after these operations we got the transform point with respect to that new shift positions, new origin, but we have to restore the original situation. So, in that case we need the inverse translation. So, step 3, then translate back to hk, translate back, because in step 1 we got all the points are translated by some amount. So, we have to give translate back to hk, we translate back 0 0 to hk, that is translate back this new positions A to hk, that is this is nothing but inverse operation of step 1. So, this is inverse of step 1. So, if we consider this OA as vector V. So, we can call this operation step 1, operation in step 1. We are translating A to origin. So, this is opposite to the direction of V. So, we can call this transformation operation as T minus V, because we have considered V, as this one, that is HI plus Kj, HI plus Kj. So, that is our V. And this rotations in step 2, that we can represent as rotation with respect to origin through an angle theta. And the step 3 is nothing but translation along V, because this is inverse of step 1, that is TV. So, to obtain these composite transformation operations, we are first operating step 1 on P. So, on P, which we are operating first step 1, which is T minus V. On the result, we are applying step 2, that is rotation through an angle theta with respect to origin, r0 theta. And then we are applying step 3, that is translation along V, and that is operated on this result, and this is your P dash. So, P dash is obtained by concatenating these 3 matrix operator in this order, and we call this P dash is, this is the composite operator, that is rotation through an arbitrary point A by an angle theta. So, rotation through an angle theta with respect to this arbitrary pivot point A, and that is operated on P. So, this rotation operator will be obtained just by multiplying these 3 known matrices in order. So, this is basically the concatenation of matrix operator, and these matrices, if they are multiplied, then we can get the composite matrix operator. And these matrix operations, as we know, that is not commutative, but this is associative. So, we can either multiply TV with r0 theta, and then with this result we can multiply T minus B, or in the opposite direction, r0 theta is first multiplied with T minus B, then with this result we can multiply TV. Thank you.